Okay, folks, let's get started. Before we begin, someone asked if anyone had found a passport. So could everyone just look under your seats and see if you find a passport? Okay, if you do find one, just bring it up here and I'll hold on to it, but thanks for checking. Okay, so announcements. Homework 1 is due next Tuesday. Project 1 is due next Friday. And then you can pre-scan this attendance code if you like to do that. I usually leave it up at the beginning just to make things go quicker later. But yeah, let's jump in. So to recap from last time, we talked about search heuristics. And remember, a search heuristic is a function, takes in a state, outputs a real number, and that real number is supposed to correspond to how close is that state to the goal. And when we use a heuristic like this, it can help us to guide our search through this rapidly expanding search tree and avoid doing unnecessary work by guiding our search towards useful directions. It's a heuristic that's designed for a particular search problem. So if you have a different search problem, you might need a different heuristic. And we talked about how we could design some heuristics. We talked about different heuristics like Manhattan distance or Euclidean distance, things like the index of the largest pancake. We talked about all these different heuristics. And then we talked about how the heuristic was going to just sort of give us an estimate of how we were doing in our search. Were we close to the goal? Were we far away? We also looked at a couple of search algorithms. We looked at cost-guided search. We looked at heuristic-guided search. And then we put the two together, and we had sort of this F-score, this cost and heuristic-guided search. And that was kind of the best of both worlds, right? Because uniform cost search tends to explore in all different directions, and it ends up wasting a lot of time by being overly cautious, overly patient, just trying out everything, make sure we don't miss anything. And greedy best first search just charges headlong towards the goal, which isn't always what we want either. Sometimes we want that, right? Sometimes we don't care about if we have an optimal solution. We just want a solution as fast as we can find one. And greedy search can sometimes get us there. I've used greedy search in the past. But sometimes what we want is an optimal plan. And A star is a nice blend of these two different algorithms. It searches out a little bit for low-cost plans, but it also tries to guide the search towards interesting plans. And we proved that it's optimal, provided one thing, that the heuristic was admissible, right? So we talked about admissible heuristics, this idea of like optimism versus pessimism. If we're too pessimistic, if we're just like depressed about our search all the time, we're not going to bother trying stuff because it's just so much effort. That just doesn't look, like if we're always pessimistic and our heuristic is always overestimating the cost to the goal, then we might be too depressed to even bother to expand certain states, and we might miss out on optimal plans that we would actually like to explore. But if we're optimistic and we always underestimate the cost of getting to the goal, then we'll try everything, everything's optimal, and we're good to go. So towards the end, we talked about this 8 puzzle, which is another sort of non-2D navigation planning problem. And we talked about some heuristics. One of the heuristics was, and these heuristics are just like solutions to relaxed versions of the problem. One of the heuristics was just cheating, right? You could move the tiles in one step, and moving the tiles in a single step to exactly where they need to go is a lot easier than solving the original problem. So this is like a nice relaxed version of the problem. We also talked about, like if we have Manhattan distance on the tiles, right? So I drew this picture, but I'll draw it again. Like if the 7's out of place here, and we know the 7 needs to go to this particular spot, right? We can draw the Manhattan distance to where the 7 needs to go, and then we can do that for all the tiles, and that's another heuristic that we could use. And then we talked about a third heuristic, which is the actual cost, and we said that is ideal, but of course it's not something that we could know when we're doing the search because we have to solve the planning problem before we can actually find this exact cost heuristic. So there's this spectrum of heuristics. let's play with this a little bit more. I felt like we didn't get enough chance to do that last time. So let's talk about designing a heuristic for this problem where we have a knight in a chessboard and we want to move it from some starting state S to some goal state G, right? And we want to minimize the number of moves it takes the knight to get from S to G. So if you've played chess before, even chess experts sometimes struggle with how many steps is it going to be to get from one side of the board to the other. Of course, this board is not your average shape of chessboard, but that's okay. We can handle it anyway. So yeah, does anybody have any ideas for heuristics that we could use to solve this problem? Who's got ideas? Remember that the knight moves 2 squares in one direction and then 1 square in the orthogonal direction every time it moves. So it moves 3 spaces, but 2 up and 1 across, or 2 across and then 1 up. Or it could be down also. Yeah. So how do we think about this? What do we think might be some good heuristics for this problem? Yeah. Yeah, okay, good. So we want to get, as we get closer to the goal, we'd like the heuristic to be smaller. That's a good principle to follow. What else could we try to ensure? Yeah. The Manhattan distance between the position of the knight and the position of the goal. Okay, so what's the Manhattan distance between the knight and the goal? We have to count squares, right? So we can count squares, that's no problem. So the Manhattan distance. So we have 1, 2, 3, 4, and then we have 1, 2, 3, 4, 5, 6, 7, 8, 9. I think it's 9, yeah. So that's 4 plus 9 is 13, right? So 13. Is this an admissible heuristic? Or can we figure out how to make that an admissible heuristic? We could divide by 3. Why would we divide by 3? What's the significance of 3? Yeah, okay, nice. So we just said, it's 13 steps to get to the goal in Manhattan distance. But remember that the knight can move 3 Manhattan steps at a time, right? So we could divide the Manhattan distance by 3, and that might give us an admissible heuristic, right? So we could take the Manhattan distance and divide by 3. Nice. So what is the Manhattan distance divided by 3? So if this was, I think it was 14 or 13. So if we divide that by 3, what does that give us? Something like 4 and a little bit. 4 point something. Can we ever have point something moves? So what could we do to this heuristic? Yeah, we could either drop the decimal or we could round up. So if we drop, it's definitely going to be admissible, right? Because then we're underestimating an underestimate, right? So that's nice. But yeah, what if we round up? Would that work? What do people think? Is it okay to round up? Well, let's say that we wanted to do it in 4. What would the 4 moves be? Could we get there? 4 isn't quite enough, right? So if we only do 4 moves, then we haven't covered the minimum Manhattan distance. We've gone 3 steps. Even if we go directly towards the goal every step, we get 4 times 3 is 12, and we said it was like 13 or 14 steps. So that's not going to quite get us there. So we definitely need to round up. So we can have another admissible heuristic that is rounding up, and that's going to be a slightly more accurate heuristic. Okay, what's another thing that we could do? So what do you notice about the colors of the squares, S and G? They're different. And what do you notice about the colors of the squares that a knight moves from and to when it moves? Also different. So now what should we be thinking about? If the color of the square I'm moving towards is the same color as the square I'm moving from, S and G are the same color, how many moves am I going to need to make? Yeah, so if they're the same color, it's an even number of moves, and if they're a different color, it's an odd number of moves. Does everybody see that? So we don't have to necessarily just round up to the nearest integer. We could actually round up to the nearest integer that has the right even or oddness, the right parity. So we could actually improve on H1 by rounding up to the correct parity. So in this case, because it's odd parity, we have to switch colors, we would round up to 5. But if it was the same color, we could even round up to 6. Okay? Does everyone see that? Yeah, what's another heuristic that we could use? We've talked about Manhattan distance. Yeah, what about Euclidean distance? Would that work? That would work. Yeah, why not? We could put Euclidean distance. I'm spoiling it. So why do we have to divide by square root of 5 now instead of divide by 3? What's the square root of 5? Does anyone know? Yeah. Yeah, 2 squared plus 1 squared is 5. Square root of 5 is square root of 5. So if we divide by the distance that the knight can move in Euclidean distance, then that'll give us a nice thing that we can normalize by, and now we'll have an admissible heuristic again, okay? And that, if we divide by the square root of 5, we're probably going to get a fraction again, right? Or we're probably going to, it's going to be irrational anyway, but, so what do? The same thing. We round up to the correct parity. We can do the exact same trick, and we get another heuristic. Anything else we can do? Oh, question first.
The square root of 5, did it come from the knight move or the whole thing?
Yeah, so that's the Euclidean distance of the knight move. Let me draw it in there. So we have 2 here, right? 2 in one direction, and then 1 in this direction. So we draw 1 squared plus 2 squared, and then that gives us this, which is 5 squared, right? So square root of 5 is the distance on that edge. Yeah, so what else could we do? How many moves it takes the knight to reach the squares nearby. So what do you mean by that? Yeah, so we could do this. We could pre-compute some parts of the solution. We could pre-solve. Sometimes in chess we use like opening books, or we use like lookup tables or endgame tables in order to like speed up the search. Once we get to a state that we've already memorized the solution for, we can just look up the solution in our table and we know the exact solution. So yeah, that can be a useful thing to do. If you know you're going to solve the same planning problem a bunch of times, you can get a heuristic that way. Is that what you had in mind? Okay. Yep. Yeah, you could take the maximum of these two. Yeah. So we talked about that last time, right? So 2 admissible heuristics, they're both underestimating, but they might have different estimates. But the maximum of those 2 estimates is still an underestimate of the true cost. So that would give us an admissible heuristic. Anything else we could do? Yeah, an admissible heuristic means that our heuristic underestimates the cost of getting to the goal from a given state. So heuristic's just a function, takes in a state, outputs a real number. If that real number is less than or equal to the cost of optimally planning from that state to the goal, it's admissible. It has to be that way for every state. Okay. Yeah, other ideas? Yeah.
What's the benefit of rounding up all the heuristics?
Yeah, so if we round up, and we know that even when we round up, we're still underestimating the cost, then we have just a closer estimate. And because we know that we can always round up, because we just sort of proved it to ourselves, that's going to be a more accurate heuristic. It's going to guide us in the right direction more often. What about if we break up the distance in x and y and think about them separately? Can we do anything there? What if we just focus on the y direction? How many steps would it take us if we were moving as fast as possible to close the distance in the y direction, the vertical direction? What's the fastest we can close that gap? Yeah. Divide what by 3? So we could divide by 3. S's y position, subtract that from G's y position, divide by 3. Why would we divide by 3? Okay, so now first it's 3. Now, so what makes you say 2 now? Yeah, so the fastest we can move up is if we take one of these blue type moves, right? Could be this, to the right, could be to the left, but like the fastest we can move up is 2 squares. So it's going to take us at least, gy minus sy divided by 2 in order to get all the way up there. And what about in this direction? What about in the horizontal direction? Well, we could take green type moves, right? Green moves that go up, green moves that go down, but no matter what, we're not going to go faster than 2 squares at a time in the horizontal direction, right? So we could look at the horizontal distance, gx minus sx, divide that by 2. So, and then what would we do with those 2 heuristics? Yeah. Could add them together. Well, we could add them together. Is there anything that might go wrong if we add them together? It might go over. It might overestimate the distance, right? Because if we say that we're going to go that way and we're going to go that way, and we're estimating by dividing this distance by 2, and then we're saying we also have to divide this distance by 2, we might be making progress in the horizontal direction while we're making progress in the vertical direction. And so there might not be that much left to do, right? If we just kept taking blue moves, we would make a lot of progress to the right, right? First we would go where he's going, and then we would go, let's see if I can draw this in blue, right? So then we would go here, right? And then we'd go here, and then we'd go here. And so now we've actually closed the horizontal gap entirely, and we still haven't finished our vertical gap. So we might overestimate. But maybe not adding. What else could we do? Someone already mentioned it with the 2 heuristics from before. We have 2 heuristics. They're both admissible. What can we do with them to get another admissible heuristic? Yeah? Say again? Maximize. Yeah. So we could take the maximum of the 2. Okay, so the maximum horizontal distance or vertical distance divided by 2, we could maximize those 2 things together. And then we could also round that up for the correct parity. And then we could take all 3 of these heuristics, and then we could maximize the maximization, right? And so now we have all these heuristics. So this is a kind of a complicated heuristic. First, we look at the Manhattan distance. We round that up to parity. Then we look at the Euclidean distance, round that up to parity. Then we look at the maximum horizontal, the maximum vertical, divide those by 2, and then round those up to correct parity, and then take the max, right? So this is a little bit more involved to calculate, but it's totally a valid heuristic, it's admissible, and it will solve this problem a lot quicker than if we had just used one of these heuristics. Okay? Does that make sense? Any questions about this? Okay, yeah, one question, yeah. Should we always go for the max value of the maximum admissible heuristic? It depends. So like this might be harder to compute, right? This might take more computational resources to compute. So if you really need a fast heuristic, you might opt for something that's a little bit simpler, and you might not want to go for the maximum every time, because then you have to do more calculations. All right. So I showed this picture last time. I'll just put it up here again, just kind of visualize. So there's ways we can compare these heuristics to each other. If a heuristic always has a higher estimate than another heuristic, then it is closer to the true cost. So if HA always let's say that they're all admissible heuristics, they always underestimate the true cost, but A sometimes has a bigger estimate than C, then we would say that in those situations, A is more accurate. And if A is always more accurate than C, then it dominates C. So I just wanted to cover that again, because we kind of went through it quickly last time. And you can form heuristics that dominate other heuristics by combining two heuristics, even if those two heuristics don't have a relationship between them, right? Like A and B, you're not sure if one, sometimes A says it's bigger, sometimes B says it's bigger, but you can maximize the two and then you'll still get an admissible heuristic. We also talked about the zero heuristic, which is the trivial heuristic. Totally valid, it's admissible, because it always underestimates, it always says zero. Zero is always an underestimate. And if we have an admissible heuristic, we proved that A star search is optimal, but there's a caveat to this. And we've seen this crop up a few times, but we haven't really dealt with it yet. So what can happen if we're expanding a search tree? Let's look at this particular state graph where we have nodes A, B, C, D. A has two actions that come out of it. We can go left or right. Maybe they have different costs, so it's important which one we take, right? And given that we go from A to B and then we get to B, we have two actions we can take, left and right. Maybe they also have different costs. So our search tree looks like this. A has two children. A's children have two children each. Each of B's children has two children each, right? And you can see that this is growing exponentially. This search tree is getting really big really fast. If we have to store this whole thing in the tree, that's going to be really memory intensive. And another thing that can go wrong is if we ever find the same state that we already saw, like if D ever loops back to A, well then we're stuck, right? Because now we're going in circles and the picture looks kind of like this, right? So we're walking around in this maze and suddenly we realize that we're retracing our own steps, we're duplicating the work that we've already done before, and we would like to avoid that because it's kind of a waste of effort. So this is where graph search comes in. And just to sort of drive this point home, let's imagine that this is our search tree, right? Well, you might notice that this subtree, this starts with node E, and this subtree, which also starts with node E, they're the same subtree, right? So, and they might be infinite subtrees. So why do we store both of them? Well, we store both of them because there's different paths in the search tree that get us there, and we didn't want to miss out on possible better paths. But if we only store the best path to get to E, then we don't have to expand E both times. So this is kind of the principle of graph search. And there's other nodes in here that are also duplicates, right? So P is duplicated, there's this P, and then there's this P, and all these could be like infinite subtrees. So the idea with graph search, never expand a node twice. If you've expanded it already, that's the only time you need to expand it. Okay? So how would this work? Anyone have ideas? Yeah.
You could maybe have like a table or a dictionary of the nodes or states you've already explored.
Yeah, we just got to keep track of what we've seen already, right? So let's do that. We're gonna do tree search the normal way, except now we're also gonna keep track of what we've already seen. And as we're expanding nodes in the frontier, we're gonna check if we've seen that node already. If we've seen it already, we don't expand it. It's as simple as that. If we haven't seen it, then we put it into our list of nodes that we've seen before. We call these the closed set, the set of nodes that we can close the book on. We don't need to open that again. If we've expanded it once, it's in the closed set. And if we expand a node, we put it into the closed set so that the next time we see that node in the graph, we don't open it again. Okay? And we have to store this as a set rather than a list, because a list, we're going to have the same problem. If we keep exploring the tree, we might see the same node many, many times. We might see it an infinite number of times. We don't want to store all of those instances in the tree. So we store them as a set, then we don't have duplicates. Okay, so we should be thinking about this. We should be thinking like, okay, we're changing the algorithm. Is this going to have any consequences for the proofs that we already made, right? Can this wreck completeness? Are we definitely going to find solutions? Is it going to be optimal anymore? Like, how do we know? Let's look at an example. So this is an example that we kind of saw before, but now I've changed the arrows so that they're two-directional arrows, right? So before we couldn't have loops because we didn't know how to handle that in the tree, but now we can do it. We can do loops. So this A star is gonna work the same way as it always works. First we think about our search tree, and now we're gonna have a closed set also, right? The set starts out empty. We haven't explored anything yet. And first we put S in there. It's A star, so the heuristic plus the cost to get to that node is what gives us our F score, right? 0 for getting there, because it's the starting state, plus 2, the heuristic. We expand S to get SA and SB. Where now, I used to write just A and B, but like now the path to getting to that node is going to matter, so I wrote it in there. So we got 1 to get to A plus 4 heuristic, and then 1 to get to B plus 1 heuristic. So that's our new frontier, right? This is our frontier. What do we expand first? SB, right? Lower F score. But we also have to put S into our closed set, right? We just expanded S, right? So S goes into our closed set. That's very important. And now we're going to expand SB. So these are the children of SB. What are they? SBC and SBS, right? We have a loop already. SBS, this path. It costs us 1 in each direction. That's 2 plus the heuristic at state S, which is 2. So that's 2 plus 2. And then SBC is 1 plus 2 plus the heuristic at C, which is 1, which is so 3 plus 1. So now this is our frontier, our fringe. Okay? What else do we have to do? We've just expanded B. We've got to add it to the closed set so that we can keep track. Every time we expand a node, we got to add it to the closed set. Okay, so what's the node on the frontier that's the lowest cost? SBS, SBC, they're sort of a tie, right? Let's suppose that we were going to do SBS, because then we can get to the interesting part. Well, we think about expanding SBS, and we say, hold on a second. We already saw S. That was the red circle up there. It's in our closed set. We shouldn't expand S again. We'll just be back where we started. So we can cross that one off of the list. We don't expand it. Okay, now what's next? SBC. That was the next lowest cost, right? Or is the same cost. So we expand SBC. Okay. Those are its successors. Anything else we have to do? Add it to the closed set. We just expanded another node. We put it in the closed set. Great. Okay, now what? This is our frontier. What's next? SA, right? SA is the lowest cost. Okay, have we expanded A yet? No? So expand A. Great, that's SAC. We can cross this one off. That's our fringe now. What do we have to do? Add it to the closed set. Okay, nice. Good, you're getting the hang of this. All right, and now what? What's the next lowest F score? SAC. Should we expand SAC? No, why not? Because it's in the closed set. Okay, so cross that off the list. What's next? SBCB or SBCG, they both have 6, right? So we can cross this one off too, right? Because it's also in the closed set, which leaves us this one, that's the goal. Okay, so we're expanding the goal node. We're good, we declare victory. Are we good? No, why are we not good? So we're taking this node off of the fringe. It's not like we're putting it onto the fringe, right? So when we dequeue a goal node, we should be okay, but what's happening here? Yeah. It's not the best route. I thought A star is supposed to give us optimal plans. What the heck? So why did this happen? The idea of an admissible heuristic was that we always want to be underestimating the true costs. And now that we've added this graph search thing, now that we've added routes that can go in different directions, and now we're taking nodes out of consideration because we have this closed set, things are going to work a little different. So the main idea is the same. We still want to estimate heuristic costs when we have heuristics. We want them to be underestimates. So that was admissibility, right? It says the heuristic cost is less than the actual cost to the goal. But what about between the nodes, right? So if we have a node A, okay, this is admissibility, right? So h of A underestimates the actual cost, which means h is 4, g is here, this estimate has to be less than this actual cost, right? And for 4, it is. This is taken right out of the last graph, too. But one thing that we can't say is that the heuristic is estimating the costs of the actions by underestimating them. So what does it mean to have an action cost, an arc cost? So an arc is just like any sort of, it could be a single action, it could be a collection of actions in a direction. Like if we're underestimating all of those costs, we have a consistent heuristic. And if we're sometimes overestimating those costs, it's an inconsistent heuristic. This is a different concept from admissibility. So admissibility says, I only just care about estimating the cost from any node to the goal. And then this idea is saying, this could be any node to any other node. I want to make sure that I can underestimate those costs. But this is kind of a weird idea, right? Like, what does it mean for a heuristic to underestimate the cost of an action? A heuristic is a function that takes in a state. How can we estimate the cost of an action using a function that estimates the cost of a state? Let's say we want to do this action, A to C. We have a heuristic for A, a heuristic for C. If we take that action, we know its true cost is 1, but what does our heuristic think that the cost might be? Well, if it goes from h equals 4 to h equals 1, the heuristic is kind of saying that the heuristic of that action is 3, right? So the consistency property says that when you subtract these things from each other, they underestimate the cost of the action in between. So that's not the case here. We would have to change this a little bit to make that be true. This is also known as the triangle inequality, if you rearrange terms, right? So one side of the triangle, this side from A to G, is the first heuristic, right? That's this piece. And then the other two sides of the triangle have always got to be larger or equal to this first side, right? So you go around a triangle and you take two sides, that's always going to be greater than or equal to the distance from the first side. That's the triangle inequality. So this heuristic won't get us there, but we could modify this heuristic to get us there. By the way, the true cost always satisfies the triangle inequality. But yeah, so we could modify this to get an admissible and consistent heuristic. We could change h equals 4 to h equals 2. H equals 2 is still an underestimate of the cost from A to the goal, right? 2 is less than 4. But now when we subtract 1 from 2, we get an action cost estimate of 1, which is equal to the cost of the actual action. Some consequences of consistency are that if we have this property, then the f value along a path never decreases. And A-star graph search is optimal. I'll sort of sketch that in a second. But let's go back to this example. Let's change the heuristic value for A from 4 to 2. And let's just check. Is this consistent now? Well, we already looked at this edge. What about this edge? That's the only other one we would have to think about. Is that consistent? H is going from 2 to 2 along a path of length 1. So what do we think the action cost is under this heuristic? Heuristic's saying 0 because it's 2 on both sides, right? So here the heuristic is 2, here the heuristic is 1. It's estimating the cost of this action to be 1. That's an underestimate. Here the cost is not changing. The heuristic is not changing, so the cost of this action is 1, but the heuristic says I estimate it to be 0. That's also an underestimate. So this is a consistent heuristic. You can check the other ones for yourselves. So we'll do the same thing again. We have our search tree, we have our closed set. We put the starting state on there. We expand to get its children. Notice that there's a 2 there now instead of a 4. And then what do? We could expand its successors, but what do we have to do first? Add it to the closed set. Okay, then we expand its successors. Great. Now we have our frontier. What do we expand first? A. Wait, first we got to add it to the closed set, right? So then we expand A. We have SAC. Now we have a bunch of options. We could do SAC, SBC, SBS. SAC looks like it's the lowest cost, so we can do that. What do we have to do first, though? Add A to the closed set. Okay, nice. Then we can expand this. And then, so now our frontier looks like it's these 5 states, right? This is our fringe. Okay, that's a lot of choices. What's the lowest cost? SBC, SBS, those look like they're a tie. Anything that we should consider? Well, SBS is on the closed set, right? So we can cross that out. Oh, yep, I forgot. We have to add it to the closed set also. See, we just opened C. So now let's look at SBS. It's already in the closed set, so we don't need to deal with that. And now what else? C is in the closed set. So this is our duplicate of that big branch, right? This is SAC versus SBC. And the higher F score is getting expanded second, and it's not getting expanded because it's in the closed set, so we can ignore that. So this kind of fixes the problem, if you can see that from before. I'll have another slide in a sec comparing the two. But then we just keep going. We cross this one off because we've already expanded it. We cross this one off because we've already expanded it. This is the goal. Now this is the only thing in our frontier. We pull it off, and we declare victory. So consistency implies this non-decreasing F-score property. And so when we had an inconsistent heuristic, we got a tree where this red path, S to SA to SAC, goes from F-score 2 to F-score 5 to F-score 3. So this is like a roller coaster ride. Our heuristic, we're following it. It's saying, this is the right way to the goal. So I follow my heuristic. And then it says, actually, no, maybe that's the right way to the goal. And so I follow my heuristic over here. And then it keeps changing its mind about what's getting better and not getting better. So that's an inconsistent heuristic. You don't want to follow a compass that keeps telling you north is different directions. But if you have a consistent heuristic, this is what the path looks like. You start with 2, you go up to 3, you stay at 3, then you go up to 5. This is a non-decreasing path to get to the goal. And this is true for all the paths in this tree. So that's really nice. And when we have a non-decreasing F-score, that's what's going to get us this optimality property. How's that going to work? Well, let's consider what A star does with a consistent heuristic. It's going to expand nodes in increasing total F-score. So if this is the picture of our search tree, first we're going to expand all the nodes with F-score less than or equal to 1. Then we're going to expand all the nodes with F-score less than or equal to 2. Then all the ones with F-score less than or equal to 3. And this will just keep going. At some point, we will reach a goal, and it will be the one with the lowest F-score. But when we reach a goal, what is its H-score? H is the heuristic. What is the heuristic of a goal state? 0, right. So if we reach a goal state and it has the lowest F-score, it also has the lowest G-score, the cost to getting to that node, which means it's an optimal goal. So that's great. So we get optimality. So fact 2, for every state, nodes that reach n optimally are expanded before nodes that reach n suboptimally. And that's what gets us optimality. Okay, a little bit less of a proof than the last time, but hopefully you'll take my word for it. Yeah, so A star tree search is optimal when we have admissible heuristics. A star graph search is optimal when we have consistent heuristics. And when H is 0, this is the trivial heuristic, we recover uniform cost search in both cases, and it's special cases of each, but H equals 0 is also consistent because it's underestimating all the action costs. 0 minus 0 is always 0. So uniform cost search also works on graphs. So that's great. Also, consistency implies admissibility because in order to be admissible, you just need to underestimate the cost of the arc from the node you're at all the way to the goal. For it to be consistent, you need to underestimate the cost of every arc. So obviously you have to be admissible if you're consistent. It turns out that if you just design heuristics by trying to do these relaxed planning problems, you'll often find that well, they'll generally be admissible heuristics, but they'll tend to be consistent as well. So it's not that hard to, it's actually harder to design an admissible heuristic that is not consistent sometimes than it is to design one that is. Okay, there was a question, yeah. Yeah, so an arc could just be a single action. So that's the simplest version of it. So we want to estimate the cost of a single action by subtracting the heuristic at the second node from the heuristic at the first node, and that's our action cost. And an arc cost just says it could be some other number of actions besides one. So we go from node A to node C by way of node B, and we add their two costs together, and we want the estimate of A's heuristic minus C's heuristic to be less than the cost of going from A to B and then B to C, the optimal way. So if B was an optimal middle node on that path. Yes, right, exactly, yeah. So if we defined the heuristics in such a way that it was not consistent, that would show us that we're going on a non-optimal route, yeah. And then we don't get optimality. Yes, question? Ah, yes, the triangle inequality. So does one of the nodes have to be the goal state? It does not. So it could be A, B, C, and none of those is the goal. But from A to C, the heuristic change from A to C, meaning H of C minus H of A, has to be an underestimate of the cost from A to B and then B to C. Yes? Well, I just happen to know that would work. You don't always know which one's gonna fix it, but if you design your heuristic in the first place to be consistent, by making sure that you try out a couple of short little plans and make sure that like you're always underestimating action costs, or you could try to prove that you're always going to underestimate action costs. So that would be the best way to get a consistent heuristic. But as I said, like usually if we just take a relaxed planning problem, we're going to get not just an admissible heuristic, but also a consistent one. So that tends to just work out for you. Yeah, more questions? Yep.
If it's admissible and consistent, is it more optimal, or is it just like one or the other?
If it's consistent, it's admissible for free.
Oh, it implies that, right?
Yeah.
If it's just consistent, it doesn't imply admissible.
If it's consistent, it implies admissibility. If it's admissible, it doesn't imply consistency necessarily.
Okay, so only playing one.
Yeah. So admissibility, again, this is just saying I estimate the cost from any node to the goal by underestimating. And then consistency says I estimate the cost from any node to any other node, and that's an underestimate. So some of those nodes are goals, so in order to be consistent, you have to be admissible. Okay. More questions before we move on? So great, we're optimal. That's nice, but we might use a lot of memory if we do this. Even if we have this graph search optimization, A star keeps the entire explored region in memory, right? We have to keep track of this frontier. We have to keep track of all the paths that led us to the frontier. So there's a lot of things that we might have to keep track of at a time. Sometimes, for big planning problems, you'll run out of space on your computer's RAM before you even run out of patience. And that's not great. This makes us sad. There are variants that use less memory. So we talked about how iterative deepening depth-first search was like a nice version of depth-first search that could get you to optimal solutions, because you have to explore all the nodes of depth 1 before nodes of depth 2. We can do the same idea with A star. We can do iterative deepening A star, expanding in terms of F score instead of depth. And this can help us in memory. There's a couple of other variations that I'm not going to go into the details of. Recursive depth-first search that uses an F limit rather than a depth limit. And then there's this SMA star, which just uses all the memory that you have, and it tries to just remember all the stuff, and then it kicks out stuff that has the the highest F score first when it runs out of memory, because probably those aren't going to be on the path to an optimal solution. But yeah, more stuff is in the book if you want more info on that. But one thing I want to just underscore here is that like we're still wearing two hats when we're doing search. The first hat was there's this world, it's complicated, we have to make a model of it to run a search, to build a search problem in the first place. We have to decide what the states are going to be. We have to decide what the actions are going to be. What's our successor function? Do actions have costs? What are the costs going to be? What's our goal condition? How do we know when we're done? What's our initial state? So modeling is the first step, right? And once we have a model, we can design these algorithms. We can prove that they're optimal. But if we have a bad model, it doesn't matter how optimal our plan is. It might not help us, right? So this goes wrong in the real world whenever we forget that the model is not the real world. So this is some old mapping software from 2005 MapQuest. I think this is older than some of you, which is kind of blowing my mind a little bit. Right, so what happened here is that at some point it says, yeah, turn left on Loma Vista Place. And if we turn left on Loma Vista Place and we're in a car, this is a sidewalk, and it's going to be tough to drive down, unless you have a really small car. So what happened? Did A star fail us? I thought we had a proof of optimality. Well, no, it's not that A star failed us. It's that the person who modeled this map just put in an action where there wasn't one, right? This action doesn't correspond to a real-life thing we can do. Same thing for this map software, Microsoft Map Point. I don't even know if I've ever heard of this. From 2003, oh boy. Yeah, so this is a route to try and get from one place in Norway to another place in Norway, and to do that, we go in through Europe, continental Europe, take a couple of ferries, and then head back to Norway. Right? So in this one, we had an action that we had in our model that did not correspond to a real-life action or operation that we could take, and in this one, we have an action is clearly missing from this model, the one that takes you straight there through Norway and doesn't go through Europe. And so one is missing an action and one has an extra action. So yeah, if you confuse the map for the territory, you're going to have a bad time. So try not to do that. Just remember that a model is not the same thing as the world. Okay, I'll just put the tree search pseudocode up here, and then I'll flip quickly through to the graph search pseudocode. So if you wanted to see the pseudocode, now you've seen the pseudocode. It's in the slides. You can fetch it there later. Let's scan this code. Today's code is Olympus, because what we're going to be talking about next is called local search, sometimes called hill climbing. And Olympus was, or still is, the tallest mountain in Greece. So we're climbing this hill. We're trying to get to Olympus. All right. A couple more seconds here. Remember, this code is on the website, so if you didn't have time to scan, just remember Olympus. All right. So, yeah, so far we've been talking about these planning problems as, I just outlined all the pieces we need. We need a search space, like a state space. We need a set of actions. And what do we want to get out of an algorithm? What an algorithm gives us a plan, right? It gives us a sequence of actions that goes from the starting state to a state that satisfies our goal condition. Well, we don't always care about how we got to the goal condition. Sometimes knowing the goal state is enough. Sometimes we don't even care, right? Like there's plenty of problems like solving puzzles where just the fact that we've solved the puzzle is enough. We don't care about how we put the jigsaw pieces into place. We don't need to keep track of the order that we place them into the puzzle. So in many optimization problems, the path is irrelevant, and the goal state is the solution. We don't have to care about the path. And we can make this, so the state space is still the sort of set of complete configurations. We have to sort of define the state space somehow. But then the goal state could just be a configuration that satisfies some constraints. The n queens problem, which looks like this, is like we have constraints that none of the queens on the chessboard can be attacking any of the other queens. Queens can attack each other vertically, horizontally, and diagonally. So in this configuration, this would be a solved state. And finding these states is what we want, but we don't really care, where we moved the queens along the path to getting there. Just seeing the solution is enough. Similarly, we could be looking for an optimal configuration, the one that has the lowest cost. So like a traveling salesman problem where like we're trying to visit every city in a map or in a graph, and we want to do it in a way that incurs the least cost of getting between these cities. Once we have a plan that minimizes this, we can go off and sell whatever it is that we're selling, maybe pancakes, and then at some point, at no point do we need to know what are the other plans that we considered, right? Once we have our path, we're good. Okay? So in such cases, we don't have to worry about sort of all of the nodes that are in our frontier. We can just it's a very simple algorithm. We just keep track of one state, the current state, and then try to improve that state. That's it. That's all local search is. Okay? It uses constant space because we're keeping track of one state. And when states are really, really big, like maybe states are giant large language model neural networks, it's nice to only have to keep track of one state. And this is also more or less unavoidable if the state is you, right? So you are trying to optimize the state of yourself, meaning like learning, and constant space is pretty key. You can't imagine what different possible, you can imagine to some extent what your different possible futures are, but you can't do that to the end of time and then come back and make the perfect optimal decision for right now. At some point you're going to have to take an action in the world, and this is different, right? Before we were just trying out stuff in our heads, and once we figured out what our plan was, we would start to execute. Now we can do things online, right? We can take an action that we think is going to improve us, and then take another action that we think is going to improve us, and we can do this whole thing online. Yeah, so this is the general idea with hill climbing. We want to get to there. We want to get to that really nice goal state, this one that satisfies all of our constraints. We don't really care how we get there, but we're just going to keep going uphill until we do. Okay? So the simple idea is we start wherever, some state in our state space, and then until we get to a state that has no better neighbors, we just keep going to the best neighbor. Right? So we look around us, we say, well, this is a better state. Now I'm moving to here. And then we look around us and we say, all right, are there any better states? There's a better state, so now I'm moving to here. And then we keep doing this until we hopefully get to the top of the hill. Anyone see a problem with this? There might be a ridge, yeah. What if we get to this peak right here? That's a fine peak, but it's not the best peak. It's not the tallest peak. It's not Mount Olympus, right? It's just this little local optimum. Yeah.
So how do you determine better?
How do you determine better? Right. So you can use a heuristic. You can design a heuristic, some objective function. But yeah, you're definitely going to need something to help you evaluate height on this landscape. Yeah.
I was just going to say, right after your last question, that it was because if you look locally, like something can seem better at first, but in general, it might not be better.
Yeah, it might take you to a local maximum. Yeah, for the sake of argument, we're going to say that we totally trust our heuristic now. We say that the thing that maximizes this problem is the thing that like we always believe our heuristic, and we want to find the thing that maximizes our heuristic. Now this works great if your heuristic is we'll get into it in a second, right? So imagine like we're doing this n queens problem, right? So the state of the chessboard is that we're just going to have n queens on it. The goal is that there are no conflicts, no queens are attacking other queens. Right, so this one, there's 5 different attacks. There's an attack from this queen to that queen, from these queens to each other, blah, blah, So 5 attacks. And we want to get to a situation like this where no queens are attacking other queens. So in this case, if your heuristic is the number of violated constraints, then when there are no more violated constraints, you know you've solved the problem. So that's a totally fine heuristic. You can trust it. The states here can just be the number, that there's n queens on the board, or it could be that there's n queens on the board, 1 per column. Kind of depends on how you want to formulate your problem. Your actions could move a queen anywhere, or they could move a queen within its column, which will be a slightly easier problem. And then the heuristic function, again, is the number of conflicts. So let's describe the algorithm here. It's a very simple algorithm. We start by setting our current state to be some state, some initial state. And then we loop. For each iteration of the loop, we look at the neighbors, the successors of our current state. We pick the one that has the highest value. And then if we find a neighbor that has a higher value than our current value, we move towards that neighbor, right? We set our current state to be equal to the neighbor state. But if it's less than, if the best possible neighbor is less than our current state, or if it's equal to our current state, then we have not found a higher point on our landscape, and so we just return the current state. We give up. We quit. Quit the search. So this is kind of like climbing Mount Everest in thick fog with amnesia, right? Because you can't see where you've come from. You can't see really where you're going. All you can do is put one foot in front of the other and hope that it's uphill. Well, that sounds a little bit challenging. Yeah, what are some of the challenges, right? So we could initialize our current state to here and then climb the hill. And then we get to this local maximum. And then we look at the neighbors around us and we say, well, nothing looks better than this. None of my neighbors has a higher value than me. I'm terminating the search. And then we didn't find a global maximum, right? That's where we want to get to. But if we initialize here and we just climb the hill, we won't get there. We could also have one of these situations where we have a plateau, or we could have a shoulder, which is like it's flat, but it goes down on one side and up on the other side. Yeah, all of these are going to be challenges if that was the algorithm we take. One easy fix is you just try again. Random restarts. So we initialize to some arbitrary initial state. We could have initialized to a different one. Why don't we just try that? Maybe we initialize over here, we go up the hill, we find the global maximum, we're done. So random restarts are very effective. They find the global optimum if you do enough random restarts. Sort of trivial, right? Of course they do. But it works, so we might as well keep it in mind. And if we get into one of these situations where we have sideways neighbors, right? Well, on the shoulder, it would kind of be nice if we try some of those neighbors, because eventually we'll get to this part, and then we might start going up the hill. So we could try some like random sideways moves and just see, does this help? Maybe we have some number of sideways moves we allow. Maybe we have some probability that we're allowed to take a sideways move. This allows us to escape from shoulders. That makes us happy. It doesn't help us for plateaus, right? If it's a local maximum, we're still sad. But this could help us, maybe. Let's look at hill climbing on the 8 queens problem. Oh yeah, question. Oh, so that's saying, right. We initialize our algorithm, hill climbing, with a state. What's the state? We just pick a state. Doesn't have to be any particular state, arbitrary. So if we pick a bad state, like this state, and we climb the hill and we get to a local maximum, well, maybe we just shouldn't have picked that state. So if we pick another state, just randomly choose a state from your state space. Maybe we pick this state, we go up the hill, we find the global maximum, right? Maybe we pick this state, we go up the hill, we find the plateau. But if you do this enough times, you're guaranteed to find the global optimum.
Is there like mathematical theory behind how many restarts you need? Or is it just like you just kind of send it?
Yeah, so if you look at like the smoothness of the function and you think about sort of like what the local landscape looks like, you can probably prove how many you would need. In general, this might be a little tricky, so you just pick some number, and if it seems to be doing great in practice, then that's good. Yeah.
Could you just do like the probability of getting all the points? Like 1 over every point on the
You're saying start based on the probability?
mathematical theory, like to get the top, like 1 over, like the chance of getting every point when it's not the chance of finding the global maximum?
Could be, yeah, but there could be an infinite number of points. You could have a continuous state space, so then the probability of sampling any particular point, even the global optimum, might be 0, which would be tough. Okay, so let's look at the 8 queens problem. And let's just say no sideways moves for 1 second, right? So if you don't allow sideways moves, and you run hill climbing, and you initialize the state randomly, you will find the global optimum, or a global optimum, really just any solution to the puzzle, with probability about 1 in 7. So that's actually kind of good. So that means on average you run this 7 times, and then you probably have a solution. Okay? If you run it 7 times, you might not have a solution. You might have to go again. But yeah, so that's nice. The average number of moves per trial turns out to be about 3 before you realize you've stuck, and 4 if you've succeeded, which is not that many moves. So we could calculate the expected total number of moves needed. So this ends up being a geometric distribution. It's like the expected number of iterations before we find a success is 1 over p, and then the expected number of failures before the success is 1 over p minus 1, which is the same as this 1 minus p over p. And each one of those failures costs us 3, and each one of those successes, which is only 1 success, costs us 4. That ends up being about 22 moves on average. And then, okay, now we can allow sideways moves, and we have to decide how many sideways moves we're going to allow. So we have this knob that we can turn, and maybe we add more, maybe we add less. Let's say we're going to allow 100. This will now succeed with probability 0.94. The expected number of moves will end up being a lot more because we're allowing sideways moves. So part of the reason we're more successful is that it takes us longer, but eventually we find the solution. So 21 when succeeding, 65 when getting stuck. So this is an average of 25 moves now to find a solution. So this is a little bit annoying because we added this parameter that was supposed to help us avoid getting stuck, and by allowing ourselves these sideways moves, I mean, we're allowing ourselves a lot of sideways moves. 100 might be too many. But what's the right number for our search? We don't know that in advance because we haven't run the search yet. So now there is this irritating knob that we have to turn in order to make the number of sideways moves appropriate for our problem. And so you sort of tune it. You see if that helps. See if it's solving your problem quickly. And if it's not, you turn it again, and maybe that's going to be better. The moral is that algorithms that have knobs like this are irritating. Question? Yeah, a couple questions.
Clarification, is that 22 and 25 minutes in the entire, like, that you evaluate over all tries?
Yeah. So if you have to restart, and then you restart again, and sometimes you're failing along the way, and then finally you get a success, total, it's that number of moves, yeah. Yeah.
When you say that success is like probably within like you want to know that on a random starting position, run still finding and fail like 7 times?
Yes. For that problem, yes. Based on those actions and that state space, yes. How did we calculate this probability? So that was a similar question. So it's basically saying, if I run hill climbing with this state space, where let's say that the queens all have to be on distinct columns, and then I am allowed to move queens up and down in their column, those are my actions. If I just run hill climbing with no sideways moves, I will reach a state that satisfies all of my constraints with probability 0.14. So this is 1 in 7. So you can just verify this by trying it out. So that's how we got the number. Yeah. Okay. Let's keep going. So there's another algorithm. This idea of like, well, how many moves do you get? one way that you could generalize that is you say that there's some random probability that you're allowed to make a sideways move. And simulated annealing is named this way because there's this process when you have when you're making, like when you're doing metal working and you have like this hot metal, there's a process by which you cool it down in order to get the properties in the metal that you want. So if you cool it down fast, it has some properties, and if you cool it down slowly, it has other properties. Maybe it becomes brittle, maybe it becomes really durable, maybe it becomes like easier to bend and stuff like that. So depending on what properties you want, you would anneal it in certain ways and decrease the temperature with some schedule versus another schedule. So the basic idea of using this as an optimization scheme is to start with some temperature that allows you to basically make some sideways moves with probability something, and then over time you decrease the probability of making sideways moves. And actually now we're going to allow worse moves too. So if I'm on this local maximum, right, I'm allowed to look around me and not just accept a neighbor if it's better than me, which is obvious, like I would always want to go to a neighbor that's better than me, but if I happen to see a neighbor that's worse than me, but I have a high temperature, then I'm like, I can try it anyway. And so you just go for it, and you see if that helps, right? So depending on the temperature, this is kind of like you're shaking like a plastic landscape with a marble on it, and you're trying to get the marble to go to the bottom of the lowest valley. You just keep shaking it, and that's sort of like, you shake it fast at first so that it gets into like a region with a large valley, and then you keep shaking it. Obviously, the valleys would have to be converted. You flip the whole thing over and you do it upside down, but gravity would have to be flipped around too. Right, so you shake this thing and you're trying to start shaking it more slowly over time and decrease the temperature of the shaking. And hopefully you'll eventually roll that marble downhill, which means we would have climbed the hill. So that's the intuitive explanation. Gradually reduce the temperature according to some schedule. Question? Okay. Question? Yeah, so we'll get into that in a second. Yeah, so this is just an intuitive picture, but it sounds a little flaky. What if we make it more precise? So here's the algorithm. It's very similar to the hill climbing algorithm we saw before. It is a type of hill climbing algorithm. So simulated annealing, we start by initializing to an arbitrary initial state, and then we're going to do this loop. But now we have this temperature parameter, which is basically just going to control how often we accept things when they're worse than our current state. So the temperature is set according to some schedule. The schedule could look like this. It could be that we just exponentially decay the temperature, right? So we have some temperature. This is capital T. This is lowercase t for time. Right, so temperature could just like decrease exponentially, or it could start at some high value, then drop, and then we maybe bring it back up, and then we bring it drop, and then back up, drop again. Like, there's lots of different temperature schedules. Those are two examples. But so we set our temperature according to the schedule, and then what do? Well, if the temperature is already 0, then we just return the current state. That's how we end this loop. Otherwise, we set our next state to be a randomly selected successor of the current state, and then we choose whether we want to move to that next state or not. We look at the energy between these two different states. The energy is really just our objective function, but the physicists got in here and they were like, this is like a physical process, so let's talk about energies. Really, we're just looking at optimization values, right? Objective function at current value, objective function at next value, and we look at the delta between these two things. If we're making progress, right, we're going up the hill, we just accept the next state no matter what. Otherwise, we maybe accept the next state. And we do that according to this probability, which is an exponential raised to this energy difference divided by the temperature. So what this means is, let's think about this. If the temperature is infinite, this is e to the 1 over infinity, that's e to the 0, which is 1. So with an infinite temperature, we always accept. And if the temperature is really small, and the delta says that the next value is, if the delta is negative, right, so we're down here, this is saying that I'm looking at a state that's a neighbor, it's got a worse objective value than this current state. Should I take it? Well, what probability should I take it? And so this is a negative something over 0, which is, or close to 0, like really small temperature. This is a negative infinity. And so this is e to the negative infinity, which is 0. So there's no probability we would pick that. So as the temperature gets really big, we accept everything. As the temperature gets really small, we accept nothing. Okay? And so gradually we're going to go from one to the other. We're going to start with a high temperature, go to a low temperature, and slowly narrow in on regions of the search space that look good. So there are some theoretical guarantees. Basically, if you wait long enough, if you wait an infinite amount of time, and you decay your temperature infinitely slowly, there are some nice theoretical guarantees that this will eventually get you to the global optimum. I'm going to skip over the proof because I actually don't think it's that useful in practice. But here's what it would look like, right? So the occupation probability, this is our objective function, right? So energy means objective function. It's saying that these are the states. I would like to find this global optimum, right? This is where I'd like to eventually get to. I'm going to pick a state at random, but if I think about the long-term behavior of where my current state eventually gets to, if I have this temperature schedule, and I wait an infinite amount of time, and I infinitely slowly decay that temperature, the distribution over final states, if t is infinity, is like this. It's flat. Okay? There's equal probability on all the states because I always accept. It's just a random walk. But if t is 0, there's a spike in probability at exactly the point that's the global optimum. And then for intermediate values of t, what happens is it sort of flattens out this curve. So there's like some distribution like this for maybe t equals t1. And then if t2 is less than that, then there'd be something kind of like this. Right? So you sort of move between these two extremes. On one hand, you have a flat probability distribution, and on the other, you have a spike, and in between, you have this sort of like flattened out probability distributions. So if you have multiple global optima, then you sort of split your probability between them, which is also nice. Yeah, but the reason that I didn't go through the proof is that like there's a couple of assumptions in the proof that says, okay, one, I have an infinite amount of time to wait, and two, I'm capable of decaying my temperature infinitely slowly. So you might say like, all right, well, what's the point of proving it then, right? If I have to wait an infinite amount of time, is this a useful guarantee? Well, it's better than nothing, right? Like, if you wait an infinite amount of time and it doesn't converge, then you might get worse over time, and that would be even worse. So it is a nice to have, but like, I think it's not super practical. And if it sounds like magic, it might be too good to be true. So it's going to require more downhill steps in a row if you need to escape a local optimum. And the more downhill steps, the less likely you're ever to make them all in a row. So slowly enough might be exponentially slowly. But I will say that this is still an algorithm that people use to design VLSI circuits. And like, there's a lot of work that goes into designing these temperature schedules to make that work out. But no one can place millions of transistors on a chip or billions of transistors on a chip without some sort of programmatic help. And if you are a human who's really good at devising temperature schedules, then you can make this layout work. You put all your transistors on a chip, and this is still something that people do. So it is useful. I think we have time to cover one more thing. I'm still trying to get a sense of Berkeley time. So like, is it okay to go until 2? Or do we want, yeah, okay. All right, so we'll talk about beam search. So beam search takes some inspiration from simulated annealing, which says, or sort of the idea of random restarts, which says, if I want to make my thing work, I can just apply random restarts until it works, right? This is maybe an even more obvious and easier to prove guarantee than the proof I didn't go through. So if you want to make this thing work, you just run it in parallel a bunch of times and take the one that gets you the best objective value. Well, beam search says, I can do better than that. I can run this in parallel and allow these parallel searches to communicate with each other a little bit so that I'm focusing the search in like a tight beam. So the basic idea is we're going to run k searches in parallel. This is basically k random restarts, but run them all at the same time. But for each iteration of this algorithm, when we're generating successors, we generate all the successors from each of the k current states. Let's say that there's some branching factor, right? So if the branching factor is b, then this would generate b times k states, right? B times k. And then we choose the best k out of those b times k in terms of their objective values, and we keep those around to be the start of the next iteration. So we're always refining as we go. Now, this doesn't have to be exactly the best. Like, you can choose probabilistically, bias towards the good ones. But yeah, this is the rough idea. So what does this look like? It says if we start with k equals 4, if these are our initial states, we're running this search in parallel 4 times, and they have heuristic values 8, 8, 7, 6. Let's say the branching factor is 2, so we generate their successors, and those are their objective function values, 7, 9, etc. Then we keep the 4 best, k equals 4, so we keep the 4 best. We move those into the beginning of the next iteration, so 9, 9, 9, 8. And then we generate their successors. We keep the 4 best, and those become our new starting states, okay, for the next iteration. So beam search is sort of like focusing our search in this narrow beam, and every time we have sort of bad outcomes like these ones, we just remove them, right? And so the beam sort of narrowly tightens onto the good directions. Yes?
Does this benefit a lot from like multi-threading?
Yeah, you would want to run this in parallel, but the thing is you would then have to communicate at the end of one round just to say, okay, what did everybody get? You got some good numbers, I got some bad numbers. All right, we'll go with your numbers, right? Yeah. Yep. Yeah, that's like the elevation of our hill climbing landscape, yeah. Why do we start? So the idea is we're just going to do 4 random restarts at a time. And it could be the case that, so it could be the case that the 7 leads to an 8, the 8 leads to a 9, the 9 leads to a 10. Like, we could still, this could still end up being better than the yellow ones. Yep. So having multiple options is sometimes good. Okay? Makes sense? That's the basic idea of beam search. Why is this different from k local searches in parallel? Well, because they're communicating with each other, right? The communication allows us to say, hey, this search seems to be working out. Maybe you should, come over here where the search is working out. Your search isn't working out that great. I have better numbers over here. I'm at a local peak, right? So you can come over here. My numbers are good, your numbers are bad, let me help you out. So this communication is pretty helpful. And then all we do is we sort of say, all these searches that aren't working out, we get rid of them, right? So what does this remind you of? This is like another well-known algorithm that kind of feels like this, where we take the things that do the best and we keep them around into the next generation, and the ones that do the worst get kicked out, never to be seen again. Evolution, right? This guy came up with it, Darwin. So you can imagine like genetic algorithms, which I think I have just 1 minute. We can probably get through this. So genetic algorithms use this natural selection metaphor. And basically, we're going to run k searches in parallel. Now we have to have a representation, sort of like a genome, of a given state that allows us to split it into pairs and then recombine those pairs. So essentially what we're saying is, I have some representation, I want to break it into pieces, and then flexibly recombine those pieces to come up with new states. So each of these is a state. I don't know what this particular state means, but it's going to have some fitness, which is like our objective function. Then there's some probability that we select it. Then we cross our pairs over and develop new states. These are our successors. And then we might do some other tricks. In the genetic algorithm literature, there's lots and lots of tricks. But this is a very widely used algorithm, and people swear by this also. So that's genetic algorithms. Not much more to say on that. So thanks, and I'll see you next time.